and welcome back to History of Mathematics. We are continuing our work through Chapter 10 of Makers of Mathematics, and we're talking about Newton's circle. I wanted to follow up on the last idea where we were talking about John Wallis, who was the most prominent mathematician in England during the generation before Isaac Newton. And I wanted to discuss a second example of Wallis's procedure for finding the quadrature under the curve y equals x power m. In other words, finding the area under the curve y equals x power m. In the example we did last time, we looked at the curve y equals x, or just y equals x to the first, and that is perhaps deceptively simple. So we will look at a second higher power to get a better idea of the mechanics. So let me switch over to the document camera here. So we are looking at a crude drawing of the graph y equals x cubed. Okay, so we're talking about Wallis's procedure for finding quadrature with this as our example. And you remember what Wallis would do. He would be comparing the area under the graph to the area of the related rectangle. Now, in this case, the area of the related rectangle, well, it's not hard to find. If the base is the interval from x equals 0 to x equals a, and we're talking about the curve y equals x cubed, the height over here would be a cubed. So the area would be a to the fourth, the area of the related rectangle. In fact, let me go and put that over here. So that is area a to the fourth. Okay. So what we're going to do is get an approximation for the area under the curve and look at a comparison between that and the area of the related rectangle. Okay. So, following the procedure that we outlined in the previous video, we would take an approximation, okay, by looking at the total area of various rectangles. Let me scoot this up here a little bit. Okay, so we are taking the interval from 0 to a, breaking it up into n pieces. So each piece has total width. So the pieces have width a over n. So that's why each term here has an a over n. That's the width of the rectangle. And to get the height of the rectangle, we evaluate our function, which is the cubing function, at the endpoint. So the first rectangle, that's a over n, 2a over n, 3a over n. So that's why these terms are being cubed here. Those are the heights of the various rectangles. All right. Now, you can see here that each term in my sum has actually 4 factors of a. So that's where the a to the fourth is coming from. You've got 3 here and another one here. And you also got 4 factors of n down in the bottom. 3 coming from here, that power right there, and then 1 from there. So that's n to the fourth. Okay, if you factor that out from this term, you would have factored out everything, so you'd be left with a 1. Now this, you factor out everything but the 2, but remember the 2 is to the third power. Okay, so what we need to do is look at this sum, the sum of the first n cubes. And you can prove by mathematical induction that 1 cubed plus 2 cubed plus 3 cubed all the way up to n cubed is equal to n times n plus 1 divided by 2, whole thing squared. All right, now if we do the math over here, I would have to square both of the terms. I'd have to square this, I'd have to square this. Of course, I also have to square the 2 downstairs. So I get this. Expand out this, and you get n squared plus 2n plus 1. Distribute through a factor of n squared, and you get this right here. Break up the fraction, and you get this. And this tends to 1/4 a to the 4th as n goes to infinity. Okay, and that's of course what Wallis would have cared about. He would have cared about the ratio of the area under the curve to the area of the related rectangle, and we can see in this case that the area under the curve is 1/4 the area of the related rectangle, because we showed just a second ago that the area of our related rectangle was 1/4. And remember, what Wallis's goal was to generalize this to find the area under the curve y equals x to the m, no matter what the value of m was. And he did kind of go and generalize that, and he was able to say, okay, well, the ratio of the two areas is 1 over m plus 1. The area under the graph of y equals x to the m from 0 to a is 1 over m plus 1 times the area of the related rectangle. So that's pretty much all we will be discussing about the work of John Wallis, and we'll continue our work through Makers of Mathematics Chapter 10 and talk about the contributions of Isaac Barrow, and we will have a link to that down over there.